In this lecture, we are going to see some examples for checking how the function is regular. Consider this problem. Show that the function f of z equal to root of modulus of xy is not regular, that is not analytic at the origin, although the CR equations are satisfied at the origin. So here you have to find out the function which is not analytic at the origin, but the CR equations of Cartesian form satisfied. So how to prove this? Given function is under root of modulus of xy. So here by equating this to u plus iv, you will get real part is under root of modulus of xy and imaginary part we are having 0. So as by CR equation you have to find dou u by dou x. Dou u by dou x, what is the formula? In limit u of x plus del x comma y minus u of x comma y by del x. Now you have to find what is the value of ux at the origin, because they are saying that this function is not regular at the origin. So you are finding ux at the origin, that means x equal to 0, y equal to 0. By substituting it, you are going to have u of del x comma 0 minus u of 0 comma 0. Wherever x, y comes here, you are going to put 0 here. So you are getting u of del x comma 0 minus u of 0 comma 0 divided by del x. You know that what is u? U is equal to modulus of xy. Okay, so put u of x comma y means you have to put x equal to del x and y equal to 0. Therefore, this gives you 0 here. So, uy of 0 comma 0 also you can able to find it in the similar manner. It is equal to 0. Vx of x comma y at the origin also 0. Vy of x comma y at the origin also gives you 0. So, this shows that ux equal to vy and uy equal to minus vx, which is the CR equation satisfied at the origin, but the derivative of this function does not exist. You have to show it here. So, derivative of the function can be found out by f dash of 0 at the origin you are finding. So, limit del z tends to 0, f of this is f dash of z. So, you are going to put z plus del z minus f of z. So, here you are going to have 0 plus del z minus f of 0. So, here you are having f of del z. F of del z is going to be what? F of z we are having under root of modulus of xy. Therefore, you are going to have the del z is going to be del x into del y under root, which is modulus you have to put minus f of 0 divided by del z. Therefore, along the curve y equal to mx, consider the curve along the curve y equal to mx, you are having limit del y equal to m into del x where del x tends to 0. So, equal to under root of del y is going to be m into modulus of del x, m into modulus of del x. So, that substituting it, you are going to have under root of modulus of m into modulus of del x square divided by del x times 1 into 1 plus I into m. Substituting y equal to mx. So, you are getting this equation. Therefore, you are getting under root of modulus of m divided by 1 plus im, del x gets cancelled. Here you can see that the derivative of f of z you are having in terms of m. So, that means what? The derivative depends upon m. So, f dash of 0 does not exist. You can't find the unique limit. So, f dash of z does not exist. Therefore, f of z is not regular at the origin. Hence, we have proved that f of z equal to modulus of xy, which is under root, is not regular at the origin, although the CR equations are satisfied at the origin. Now coming into the second example, which is in polar form, we are going to see it. So consider the function f of z equal to log z. Considering the polar form of log z, z equal to r into e power I theta, you are going to have log of r into e power I theta. By using log property, you will get log r plus log e power I theta. Log e power I theta will give you I theta. So, real and imaginary part gives you u equal to log r and v equal to theta. Now, you have to find out the derivative of u with respect to r and with respect to theta, derivative of v with respect to r and with respect to theta. So, derivative of u with respect to r is 1 by r. Derivative of u with respect to theta is no theta term, so it is 0. Derivative of v with respect to r is 0. Derivative of v with respect to theta is 1. So you are having these things. Now you can check out the polar form of CR equation. What is that you are having? Dou u by dou r equal to 1 by r into dou v by dou theta, and dou v by dou r equal to minus 1 by r into dou u by dou theta. So you can check out ur equal to 1 by r into v theta. Yes, it is satisfying. And Vr equal to minus 1 by r into u theta, that is also satisfying. Therefore, you can say that this log z is satisfying the CR equation in polar form everywhere except at r equal to 0. R equal to 0 means z equal to 0. Therefore, f of z is analytic everywhere except z equal to 0. Now considering in the second problem, we have seen that f of z equal to log z, okay, is analytic everywhere except at z equal to 0. Why? If you are putting r equal to 0 here, it does not give the valid answer. So we are excluding this value of r as 0. Okay. Now come to the problem f of z equal to z power n. We have to show that it is an analytic function. Also find its derivatives. Here also we are going to consider the polar form. Put z equal to r into e power I theta whole power n. So you will get r power n e power I n theta. We know that what is the Euler formula? E power I n theta is cos n theta plus I sin n theta. Now separating the real and imaginary part of f of z equal to u plus iv, we will get u equal to r power n into cos n theta and v equal to r power n into sin n theta. So differentiating u with respect to r, you will get n into r power n minus 1 into cos n theta. Likewise, differentiating v with respect to r, you will get n into r power n minus 1 into sin n theta. Here, you are having v equal to r power n into sin n theta. Next, differentiating u with respect to theta, you will get r power n into differentiation of cos is minus sin and n theta you are having. So you have to bring this n to the front. So minus sin n theta into n into r power n. Likewise, differentiating v with respect to theta, differentiation of sin and theta is n into cos and theta into r power n. Now, you can check out the polar form. ur equal to 1 by r into v theta and vr equal to minus 1 by r into u theta. So, here these two are, this is equal to 1 by r times v theta and this is equal to minus 1 by r into v theta into u theta. So, you can observe that it is getting satisfied. Therefore, we can say that f of z equal to z power n is analytic function. Now, to find out the derivative of z power n, we are making use of this formula. F dash of z equal to ur plus I times vr by e power I theta. Substitute the value of ur and vr, which we have found out already. Then you will get n into z power n minus 1. By doing the simplification, you will get f dash of z equal to n into z power n minus 1. This is the ordinary way of finding the derivative. Okay, and by making use of analytic function also, we are getting the same derivative in this manner. Okay, here we are having the Laplace equation. What do you mean by the Laplace equation? Laplace equation in Cartesian form is dou square by phi by dou x square plus dou square by dou y square equal to 0. In polar form, you are having dou square phi by dou r square plus 1 by r into dou phi by dou r plus 1 by r square into dou square phi by dou theta square equal to 0. Next, we are going to move on to the harmonic function. A real valued function of two real variables x and y is said to be harmonic if the second order partial derivative exists, that is, dou square u by dou x square, dou square u by dou x dou y, dou square u by dou y dou x, and dou square u by dou y square exist, and they are continuous. And if they are satisfying the Laplace equation, then we can say that the real valued function of the function f of z is satisfying the harmonic equation. What do you mean by conjugate harmonic? Conjugate harmonic means if f of z equal to u plus iv is an analytic function of z, then v is called a conjugate harmonic function of u, or u is called a conjugate harmonic function of v. And u and v are called conjugate harmonic functions of themselves. Now, properties of analytic function. The first property says that the real and imaginary parts of an analytic function f of z equal to u plus iv satisfy the Laplace equation. Or real part u and imaginary part v of an analytic function f of z equal to u plus iv are harmonic function. So, harmonic function means it is satisfying the Laplace equation. Therefore, you have to prove that del square u equal to 0, and you have to prove that del square v equal to 0. So, how to prove this result? Consider an analytic function f of z and consider the real and imaginary part, and assume that the CR equations are satisfied, that is ux equal to vy and uy equal to minus vx. Then differentiating ux equal to vy with respect to x, again we get dou square u by dou x square equal to dou v by dou y dou x. Likewise, differentiating the second equation with respect to y, will get dou square u by dou y square equal to minus dou square v by dou x dou y. So, by adding these two, you will get vyx minus vxy. We know that vyx is same as vxy. Therefore, the right hand side is equal to 0. So, u is satisfying the Laplace equation. Hence, u is a harmonic function. Now, in the similar manner, if you want to prove that v is satisfying Laplace equation, considering the first equation, here you are having ux equal to vy. So, differentiate the first equation with respect to y partially, and differentiating the second equation with respect to x partially, you will get dou x dou y equal to dou u by dou x dou y equal to dou square v by dou y square, and dou square u by dou y dou x equal to minus dou square v by dou x square. Then adding these two, you will get dou square v by dou x square minus dou square v by dou y square equal to uxy minus uyx, which is equal to 0. Hence, v is satisfying the Laplace equation. Hence, if f of z is an analytic function, its real and imaginary part satisfying the Laplace equation. The converse of this result need not be true. So we can try out for the Laplace equation in polar coordinates. Second property says that if f of z is an analytic function, then family of curves u of x comma y equal to a and v of x comma y equal to b cut each other orthogonally. That means their slopes product equal to -1. So consider f of z as an analytic function. Then it satisfies the CR equation. That means dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. So here you are having the total derivative formula u of x comma y equal to a. It is given family of curve. And v of x comma y equal to b. Taking the differentials on both sides, we get du equal to 0. Differentiating u with respect to x and y, since the right hand side is constant, you are going to have 0. So by using the total derivative formula, you will get dou u by dou x into dx plus dou u by dou y into dy equal to 0. Now, what is dy by dx? You can keep this alone here. So, dou u by dou y into dy equal to minus of dou u by dou x into dx. So, this can also be written as uy into dy equal to minus ux into dx. Now, bringing this one this side, you will get dy by dx equal to minus ux by uy, which is a first loop. Likewise, you are going to find out from the second family of curve v of x comma y equal to b, using total derivative, we'll get dv equal to 0. So, this implies dv equal to 0. dv can be written as, so which gives you dou v by dou x into dx plus dou v by dou y into dy equal to 0. Likewise, in the previous step, by keeping dy by dx in the left hand side, you will get the another slope, that is minus vx by vy. So product of these two, if I am doing the product of these two, m1 and m2, you are having it is equal to -1. Hence, it says that the two curves are cutting each other orthogonally when if the function is analytic. Next property, an analytic function with constant modulus is constant. So by considering f of z as an analytic function, you have to prove that modulus of f of z is constant. How to prove this? So consider f of z is an analytic function. Therefore, it is satisfying the CR equation. Now you have to prove that modulus of f of z equal to c. So to prove that result, modulus of f of z, we know that it is under root of u square plus v square equal to c. So you can write it as u square plus v square. By squaring on both sides, you will get equal to c square. This represents the circle with center 0, 0 and radius is c. So here, differentiating this equation partially with respect to x, you will get 2 times of u into ux plus 2 times of v into vx equal to differentiation of constant is 0. So ux into u plus Vx into V equal to 0. Likewise, differentiating the same equation partially with respect to y, you will get 2 times of u into uy plus 2 times of v into vy equal to 0. From this, we are getting u uy plus v vy equal to 0. Since f of z is an analytic function, it satisfies the CR equation. So ux equal to vy and uy equal to minus vx. Now, by substituting this relation in second equation, we are going to rewrite Vx in terms of u. So ux minus v into uy equal to 0. In second equation also, we are going to write Vy equal to Ux. So the two equation we are converting in terms of U itself. Now, by solving these two equations, you will get U square plus V square into Ux square plus Uy square equal to 0. So this U square plus V square cannot be equal to 0 because it is equal to constant. Initially we have seen that. So, the only possibility is you are having ux square plus uy square equal to 0. That means what? This is a differentiation of f of z, okay, with respect to x and y. So, you are going to have f dash of z equal to ux plus I times dx. By using CR equation, you can write it in this manner. So, modulus of f dash of z is, you are going to have under root of ux square plus vy square. Then modulus of f dash of z the square equal to ux square plus uy square. What is ux square plus uy square? Just now we have found out it is equal to 0. Substituting it, we are having f dash of z equal to 0. That means f of z is a constant. Hence we have proved that if f of z is an analytic function, its constant modulus is constant. Thank you.